Hello, my name is James McKone. I'm an associate professor of chemical engineering and chemistry at the University of Pittsburgh. In 2020, I was named a Beckman Young Investigator and supported my lab's research on a project entitled Cooperative Catalysis for a Zero-Waste Chemical Economy. The research in my lab is motivated by the goal of transforming the chemical industry into an environmentally sustainable enterprise. Historically, manufacturing chemicals has followed what we now call a linear paradigm, where you start with some raw material that's mined out of the earth. You refine it into something useful to you, you use it until it degrades or wears out, and then you emit it back into the environment, say through a landfill or out of a smokestack. Our research is intended to enable a new circular approach where waste materials from chemical processes are all recovered and regenerated into something that can be used again to make important chemical compounds. When it comes to thinking about circularity in chemical manufacturing, it's really hard to overstate the potential importance of hydrogen. Let me illustrate with an example. A huge proportion of greenhouse gas emissions come from burning hydrocarbons. Burning is really a chemical reaction called combustion, where carbon-hydrogen bonds are replaced with carbon-oxygen bonds. So, if we're thinking about trying to enable circularity in a way that helps mitigate greenhouse gas emissions and climate change, what we effectively need to be able to do is to unburn chemical compounds like carbon dioxide to reverse that process. Doing that requires that we have ready access to large quantities of hydrogen that all has been generated in environmentally sustainable ways to react with the types of pollutants like carbon dioxide and regenerates the types of chemicals that we need, like hydrocarbons. Our BYI work focuses on a specific type of chemical compound called hydrogen bronze formers. These compounds are effectively rocks. They're mineral-type compounds, but they interact with hydrogen in a really unique way through a process called hydrogen insertion. Hydrogen insertion is a chemical reaction where hydrogen atoms can be stuffed into the solid structure of these rock-like chemical compounds. So what we've been doing in my lab is to examine how these types of hydrogen insertion reactions proceed, their chemical mechanisms. One of the things that we've observed in these bronze formers is that they can accommodate hydrogen insertion even when they're placed in radically different environments. For example, we can actually zap these compounds with electricity and water, and this allows them to soak the hydrogen atoms up from the water itself. We can also heat them up in a pure gaseous hydrogen atmosphere, and what we see is the exact same type of reaction occurs. We've also shown that the presence or absence of hydrogen inside of these compounds has a huge impact on their chemical reactivity. In particular, once you inject hydrogen into one of these hydrogen bronze formers, its ability to catalyze chemical transformations involving hydrogen generally goes up exponentially. This is very exciting to us because what it allows us to do is begin building catalysts and chemical reactors that function in unique ways. So we're using hydrogen bronze formers, for example, to replicate the types of behaviors that we see in biological systems, where individual steps of chemical transformations can be partitioned out between multiple specialized catalytic units. Engagement with the Arnold and Mabel Beckman Foundation over the past several years has given me ample opportunities to learn more about Dr. Beckman and his legacy. He was a remarkable person, inspiring for both of his intellect and for his business savvy. In his early career as an academic and inventor, Dr. Beckman made major advances in the development of tools that combine electronics with chemistry. This could not be more important to me personally as a scientist because my lab's focus is on electrochemistry. That is, the study of how chemical processes can be measured and manipulated with electricity. And in fact, the way a pH meter works is based on the principles of electrochemistry. And so a really significant and important advance attributed to Dr. Beckman is directly relevant to the type of lab research that we do. But I have to say that what I find the most inspiring about Dr. Beckman is his legacy of impact on people. His commitment to finding and cultivating talent and to spreading the benefits of science and engineering advances as broadly as possible. This idea both encompasses and transcends Dr. Beckman's impact on technology and commerce. And I also think that this quality is conveyed most clearly through his philanthropy and the ability of the Arnold and Mabel Beckman Foundation to support early career researchers for many years now. The BYI was one of the first sources of external financial support that my lab received back in 2020. What's been clear from the beginning is that the Arnold and Mabel Beckman Foundation was excited to get behind the vision that we had developed for this new area of study. And they've allowed us to pursue that vision flexibly to the ends that are dictated by the science. I'm really grateful for that, and I'm really excited to say also that we've been able to use BYI support to seed a much larger research program linking sustainability with hydrogen chemistry.